Thank you for joining. My name is Lifan, and I'm a data scientist at Swiss Re. So when we talk about machine learning, most topics including like regression or like classification, something like NLP or CV. But today I'm going to talk a slightly different topic on the anomaly detection and in the use case of the life insurance premiums. So while like pricing and underwriting are very core to our business, but it is also very critical for us to keep a healthy portfolio in the book. So in the past, we found that there are premiums incorrect payments from our clients. And once we find that, our business team will drill into different treaties, look at the policies, and investigate what happens here, use a heuristic approach. Although this approach works well in identifying the incorrect payments, but they are it's hard to be generalized to all the treaties. And we know it's very time consuming to look each treaty one by one in the book because like we have so many different policies in our book and usually they are very complicated. So there is the need for us to design a machine learning approach so that we can assist the business team to try out their effort into looking at the right treaties and looking into the right policies. So today I'm gonna start with talking about our analysis target and some assumptions, and then I will talk like how we identify different types of anomalies. It will be a little bit technical here, so hopefully it's not too boring. And finally, I will introduce some other anomaly detection methods that even though we don't use them, but they may be very helpful in the future. So first, what are we analyze? What are our targets? So in reinsurance, the premium has like two components. The first is the net amount at risk, or sometimes we just call it as NAR. And we also have the premium rate. The NAR is the difference between the death benefit and cash value for a life insurance policy. So although like we can work with the premium directly, we still find that it may be easier for us to work with the premium rate because we believe it is more standardized and it's more consistent. So we make this argument because of the following assumptions. So we believe that policies of the same type and with similar risk profile will have similar premium rates. By similar risk profile, we refer to the policy that are issued around the same year to the person that of the same gender, around the same age, and within the risk class, the same risk class. So on the right, there is a graph that plots the premium rates with respect to the attained age for the policyholder. And we can see that there are some points that is away from the others. So if you can see, those are the red points here. So we call this type of anomaly as value anomalies. Basically, what we do is trying to look at each policy at each duration and compare its premium rates with the other comparable ones to determine whether it is an anomaly or not. Besides, because we are working with the life insurance, we know that some plan types and structures have a very specific pattern. So here I list two examples here. The first one is the co-insurance product. So we know that for a co-insurance product, they usually have a period during which the premium rates are fixed. So the above graph here is a T20 product. We find the two, there are like 2 points looks very suspicious. Another example is a YRT product. And we know that the premium rates usually increase as the insured person ages. So the Y15 product, this graph looks very weird to us and was further investigation. And we just call this type of anomaly as pattern anomalies. So now we have defined different types of anomalies, how can we identify them? So I'm going to start with the value anomaly. So in the data set, we are given the annual data on the policy coverage level. Therefore, we can calculate the premium rate at each duration for each policy. Besides, we are given the policy information, including and policyholder characteristics. These two together can help us to draw the risk picture for the policyholder. So as I mentioned, anomalies are the data points of which the value is far from the expectation, so we can use the traditional statistics method to figure it out. Or we can even run a regression analysis to derive the expected premium rate and go from there. Another way to do it is to compare this data point with other points in the same risk cohort. But in the dataset, we don't have any labels, aka we don't really know whether it is anomalies or not ahead of time. So it is an unsupervised learning problem, and we will use some anomaly detection algorithm to do the job. Okay, so the next part will be very technical because I'm gonna introduce like 4 different methods that I'm using for anomaly detection. Okay, so the first one is called local outlier factor. It is a density-based approach proposed in year 2000. So basically, it compares the density of a sample point to its neighboring point, and tree that has a lower density as the outlier. So to define the density, we kind of need a notion of the reachability, which is highly related to whether it is the k nearest neighbor of the point or not. And then we can take the average of the reachability, and this will give us a kind of sense like how far one point is away from its neighbors. And finally, we can compare this density with respect to its neighbors by taking their ratios. And a ratio greater than 1 means that the point has a less density than its neighbors, and hence it is an outlier. So just as I described, because local outlier factor considers the nearest neighbor, it captures the local information, and therefore it is good when the density of the whole data set is not consistent. So consider an extreme case where we have a very, very dense cluster. So a point may still be considered as an anomaly, even though it is at a very small distance away from the others. But think of any other global method may fail to capture that. However, the disadvantage of this method is that the ratio itself is very hard to interpret. We cannot give it a meaning, like the magnitude of the ratio, what does it mean? There's no meaning for that. And also, this method is affected in high dimension, so it doesn't work well with the high dimensional data. So the next method I'm going to talk about is the isolation forest. It is a tree-based approach proposed in 2008. And maybe it is one of the most popular methods in anomaly detection now. So it's based on the idea that anomalies are the points that first, its value is far from the others, and second, it has very few presence. And therefore, it is easier to separate from other points. So each component of the forest is called the tree, and the way we construct tree is to trying to separate each point until we find only one value in the node. And because the anomalous points are easier to separate, we know that we only need very few separations, and hence the tree path will be very short. And this is the way how we measure the anomaly. And afterwards, we assign the anomaly score for each point, and we have a predetermined threshold to decide whether a point is anomaly or not. So isolation forest works very well on high-dimensional data, unlike the local outlier factor. We don't need to assume any distributions for our data set for our features. And furthermore, furthermore, the training set can be trained with or without any anomalies. So it's very robust. However, in the real life, we find that the implementation can take a long time and requires higher computational power if it's not appropriately optimized. The third method is called one-class SVM. So many of you may know what SVM is, right? It's the traditional classification algorithm. And it's trying to, we call learn a hyperplane that separates one class from the others. But now we only have it's called one class SVM. So what does this one class mean here? So it differs from our traditional classification problem in the sense that all the training data has only one class, that is normal. So in this case, we are not learning a hyperparameter that separates different classes, but it's trying to separate data from the origin. So if we find a new data that doesn't work well with our model, it just says, okay, this is the out of sample data or out of normal data, and it is anomaly. So as I mentioned, because we want our training set to be very normal, the algorithm is very sensitive to the outliers. So it's more appropriate for the task called novelty detection. It's slightly different from traditional anomaly detection, but in the sense that the training set is not contaminated by outliers a lot. Finally, there are two methods. I grouped them together. Both the methods here assume that inliers are generated from some Gaussian types of distribution, and we try to learn the Gaussian distribution based on what data. So the Gaussian mixture assumes that, the MCT is the way to give a robust estimation of the mean and covariance matrix so that the influence of our anomalies is minimized. And sometimes we find that our data may be not unimodal. And in this case, a Gaussian mixture is more appropriate than the standard Gaussian distribution. Okay, we are done with the most technical part. So next I'm going to talk about pattern anomalies. Yeah, so compared to value anomalies, checking patterns is more straightforward because we do know what we are expected for that policy. So most of the time we are just use a rule-based approach. So here is a very short examples here. So if we expect that the premium rates grow exponentially, we can just calculate the rate of change of the premium rates. So if indeed the premium rate grows exponentially, we know that the rate of change will stay the same across the time. So on the other hand, if we find that the rate of change fluctuates a lot, which we can measure by, for example, the standard deviation, then we know that there's something wrong with our policy. And for each coverage, we can check whether the time series pattern deviates from our expectation, regardless of our policies. But we can do one step further by comparing these metrics with other policies in the same risk cohort if we want to do some advanced checks. Finally, I'm gonna mention some other methods that we don't currently use in the pipeline. But if in the future we want to refine our models, they may be a good candidate. The first one is called autoencoders, which is a deep learning based approach. Basically, it has two components. One is the encoder trying to learn a representation of the input data, and then it tries to decipher it using a decoder. This model works well with time series data, the text data, or even the image data. But it has the same problem as the one-class SVM. We need our data to be very normal. There's no outliers in the training data, so it's more suitable for the task of novelty detection. Here is a list of like anomaly detection methods that you can find in the literature or in other projects. So starting with the statistical methods, we can use like z-score, IQR, or median absolute deviation. These are the statistics from the in the dataset. We can also leverage some visualization tools like box plot or histogram to help us to identify those abnormalities. There are also some proximity-based methods. Maybe like everyone knows about like k-nearest neighbor. It's like one of the most famous ones. There are also like cluster-based methods like k-means or cluster-based factor. Recently, there is the new invention of the copular-based method. It's good in the sense that it is deterministic. There's no need for hyperparameter tuning because it uses empirical distribution and empirical copula. We also have some angle-based method. It's more suitable for high-dimensional data or the text data when the distance between 2 points is hard to measure. And we also have other variation of deep learning, such as the replicator neural network or the GAN structure. But both of them has the same, like, share the same idea as the autoencoder I just introduced. Finally, let me talk about like 2 Python libraries that help us to do the anomaly detection. The first one is scikit-learn, like our old friend. The second one is called PyOD, which is a unified Python package for anomaly detection. The good way of it is that its syntax is unified for all the detection algorithms. It includes more than 30 different algorithms ranging from the traditional one like the isolation forest to some deep learning methods, and it also includes the latest algorithm such as the copula one. Here is the reference, covers all the methods I talked today and also include the Python libraries for PyOD. So that's it. Any questions?